Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great, good afternoon. Thank you very much for coming. This is fantastic that you're interested in the talk. We have Vladimir Barash. He's from University of Cornell. Vladimir is intern with us for the past couple of months, and he will be presenting the work that he just started doing during his internship. It's about the propagation of rumors. Vlad, it's all yours now.
All right, thank you very much. Yeah, thank you all for coming. As Natasha said, my name is Vlad. If you can't hear me, yell. I will be talking to you this afternoon about work I did with Natasha about the propagation of rumor through Twitter. So before we get to the actual study of propagation, I want to start with some background about what is rumor. And this is very important to both me and Natasha as we started out on this project, because we didn't want to begin with an overly narrow definition of rumor. So rumor can be a piece of information. It can be a cognitive process, I'll explain why later, or a social process. And we want some sort of definition that will encompass all of these aspects without being too narrow. So to that end, we focused on a very, very general definition that rumor is a particular piece of information, a particular rumor is a particular piece of information that spreads throughout a social network. And so this encompasses all of the things I just talked about. Rumor can be a cognitive process in the sense that it is collective sense-making. A group of people are talking about a rumor to try and make sense of it, whether it's true or not, what it implies, and so on. And that's one way a rumor can spread. Or it can be a social process, a conversation facilitator. So people can be talking about a rumor just to make conversation. Or it can be an emotional process, because some rumors are associated with anxiety and relief, or anxiety and talking about them, finding out that they're not true, for instance, makes you relieved. So with respect to this definition, it's very important to understand that rumor is characterized both by the information and the diffusion pattern. Information without diffusion is a set of isolated statements. There's no rumor spreading going on. There's just sort of people popping up and talking about similar things coincidentally. Whereas a diffusion pattern without information is you have some network or you have some dynamical process, but it doesn't carry any meaning if there's no particular piece of information attached to it. So now that we have this general definition, we can do a few things. We can identify pieces of information that appear to be rumors, and we can collect them, store them. We can analyze their diffusion patterns. And finally, we can come up with a formal representation of the intersection of these pieces of information and their diffusion patterns that might bring us closer to understanding what rumor really is. Now, I want to mention that the methodology we've used is on purpose very broad and captures some things that are not necessarily rumor. But without understanding this at a very general and broad level, without understanding how information spreads at a general and broad level, we can't hope to capture what it is that makes rumor rumor. A definite goal of this project down the line is to look at the data we have collected and use a combination of manual coding and so on, other techniques, maybe machine learning, to figure out which parts of this information, which pieces of information are rumors, which aren't, and what differentiates the two. So the talk is roughly going to cover these three broad goals of data collection, data analysis, and formal representation. Let's just start with the first one. So we focused on Twitter for data collection. Twitter allows, Twitter is, like many online social networks, allows people to engage in social interaction in a digital space, which is becoming increasingly popular. I'm not going to bore you with all the statistics. Twitter has something like 250 million users now, about the same scale as Facebook, and these things are growing every day. Also, very importantly, Twitter is both a social and an information network. For instance, you can have social engagement on Twitter. So Twitter users have people that what are their followers that see all of their messages. And people can follow each other and so establish reciprocal ties, and people can direct message each other or reply to each other's tweets, and so have set up social relationships. But it's also an information network. This follower relationship implies that any piece of information you tweet, any message you write on Twitter is seen by all of your followers. And there are propagation mechanisms that help this information spread, like RT or retweet. So the way a retweet works is simply you take a piece of information that you see that comes from somebody you follow, and you tweet it, you basically copy it, and now all of the people that follow you are exposed to that information, and it passes along further in the network. So these are the characteristics of Twitter. There's also a few challenges in terms of collecting the data. The data has very large volume. At this point, it's tens of millions of posts a day. Collecting data directly through Twitter meets the rate limiting through the API. So you can, for instance, if you have a whitelisted account, collect something like more than 20,000, make more than 20,000 requests an hour. And in general, the cost of collecting census-level data, by which I mean collecting all of the data that's out there and then sifting through it, that has a very high cost, and that cost goes up with time, basically on the day level. So it's not a very efficient approach. And the final challenge is identification. What is Rumour on Twitter? So how do we address these challenges? Again, like I just said, it's not a very efficient approach to try and collect all of the data that's out there if we're only specifically looking for rumors, and then try to filter that data. That's a lot of very expensive processing that we can avoid. And we do. We have 3 steps that try to address these challenges. We start with some explicit labels for Rumour. We use a query expansion approach, and we collect metadata. So what we start with is what's called the public timeline. This is just the set of all tweets that are appearing. It is presented as a stream through the API, so you don't need to grab it all. And you can sift through this stream. You can filter it with a search API, for instance, to include only the tweets that contain the string Rumour. I spelled Rumour here the American way during data collection. I spelled it the British way during the slide. Sorry about that. Right, so okay, now we have something more manageable. Tweets that contain the string Rumour are actually pretty rare. They're in the order of 1 to 0.1% of the total tweet stream, which still means we're talking about hundreds of thousands, tens to hundreds of thousands of tweets per day. But that's a little bit more manageable, and we have a starting point. Great, now we have all of the tweets that contain Rumour in them, the string Rumour in them, but presumably some tweets about rumors don't contain that string. How do we get at those tweets? Well, this is where query expansion comes in. We assume that this filtered list gives us a set of topics that are associated with the string Rumour, that is, the set of topics that are rumors. And we extract these topics with a clustering model. We use something called edit distance clustering, where we consider each tweet as a set of space-separated tokens, and we look at a classic Levenshtein edit distance between two tweets. And we create tight edit distance cliques where every tweet within a clique is x or less edit distance away from every other tweet. And these cliques approximate topics. Now, due to the nature of this clustering algorithm, the cliques are fuzzy. You're going to have a lot of overlap. Here I've presented 5 cliques that are just sort of representative of the sort of topics we get data on. One is about Harman MGM, one is about a Chinese supercomputer, Facebook webmail, boutiques.com, which was launched by Google, and Gears of War on Kinect for Xbox. And like I said, for any one of these, any one of these is a fuzzy cluster, and you might see 3 or 4 clusters with the tokens Gears, Xbox, Kinect, but slightly different variations. And if we were to analyze all of these clusters exhaustively, we'd be doing a lot of redundant work, which we don't want to do. So the way we get around that is we have another data processing step. We generate new queries, basically taking each cluster as a document and ranking terms within that document by TF-IDF, and just as a heuristic extracting the top 2 terms. And what this gets us usually is, first of all, less overlap, gets us more distinct topics. And in the case where you have these fuzzy clusters that are very similar to each other, it gets us the things that are distinctive, and basically gives us a more broad picture of a particular rumor topic. So, for instance, this one about Facebook webmail, there could be another fuzzy cluster that is Facebook webmail versus Google, and we get, here we got the 2 queries Facebook webmail, then we get 2 query terms called webmail Google, and the tweets that we collect from these query terms would be very similar and would give a broader picture. They would be similar but not identical, and they would give a more complete picture of the Facebook versus Gmail, webmail, rumor topic. So we have these query terms, and then we feed these back into the API and as new queries, and we get a new set of tweets back. These are tweets that are about our rumor-related topics, and we can begin to analyze them. Because we are here starting we are no longer searching for things that explicitly contain the string rumor, we're searching by topics. We get this notion of topic awareness. The set of tweets that is produced at this point covers all of the tweets on a particular topic, some of which may be about rumors related to that topic. So here I chose a few that were more representative of rumors, like how will Epic Games and Microsoft use Kinect in Gears of War, discussion related, etc. But you will also get, more technical things, announcements about Kinect, announcements about Gears of War, etc. And finally, we collect metadata about all of these tweets. We collect the ID of the author. We collect the timestamp of the tweet. And we collect the follow, at, reply, and retweet relationships between authors. So just to recap, follow means A follows B. It's the basic social relationship on Twitter. And it means A is exposed to B's tweets. Whenever B posts something, A sees it. At reply means A actually replies to one of B's tweets directly. This is a functionality within Twitter. And this is a sort of conversational metric. And the network of at reply relationships you would get is a more conversational network, whereas the network of follow relationships from this data set is more of an exposure network, visibility network. And finally, RT, A retweets B's message, passing the long information to A's followers, and this is more a propagation network. We're going to be focusing more on the follows network in the rest of the talk, but it's definitely in our interest to look at these other two networks as well, and we see the strength of the data collected that we can look at multiple network types for the same data. So having collected the data, we now move on to data analysis. Right, the data were collected over 1 month from the end of October and end of November. These fuzzy topics I was talking about, there we go, these guys, there were 2,400 of them during that time. The number of users, distinct users, who tweeted about at least one of these topics is about 40,000, and the total number of tweets is about 80,000. This isn't the largest data set, but in some ways that's good. As I said, we don't want to be dealing with tens of millions of tweets per day and then filtering them all. We'd rather start off with something relatively small and then work with a larger Twitter collection or ramp up our data collection activity in the future to scale up. Finally, when you look at these topics, like I said, we collected metadata for them. And using these metadata, for instance, just looking at the follows relationships, we can say, okay, here's a particular topic like Facebook webmail. Here are the IDs of all the people who tweeted about Facebook webmail. And here are the follows relationships between those IDs, between those authors. And the set of authors plus the set of follows relationships imputes a network, a potential propagation network, which the baseline, the foundation of that network is the follows relationship, basically the exposure of people to tweets. And the structure of that network is the potential propagation path, because we can identify for each person when they tweeted about the topic. And from that, we can reconstruct the time series, the ordinal time series of this person tweeted about this topic then, this person tweeted about this topic a little later, this person follows this topic, therefore we can say this person tweeted after having been exposed to the rumor from the person they follow. We can hypothesize that the rumor propagated from the followee to the follower. Like I've said, we can also look at more specific measures like retweets later on to get an even more precise notion of propagation. So I just explained these propagation network. We got about 300 of them that had at least one edge. These networks are pretty sparse. Average network size is about 15. With about 5 connected components, so there's not really a giant connected component. There usually is a connected component that is larger than others, but there are also plenty of isolates. The average network density is 0.07, and the average network diameter is 2.43. For such a small network size, 2.43 is actually not is a surprisingly big diameter. By this I mean that not only are the networks sparse, but they're also long and resemble chains rather than stars. So the path length between any two nodes in the network is actually surprisingly long, which is not what you see in many empirical social network data sets. So this is what some of these networks look like. Let me go down. So these are, of course, the largest, among the largest of the networks we collected. A lot of the networks are much smaller, but they all have one of these three general types. One type is the chain. As you can see, really long chains of propagation. Let me explain this picture, and the later network pictures are going to look very similar. So this is the propagation graph. Nodes are authors, but they're labeled with what they tweeted about. So this is about Georg and Gustav, I think 2 members of Tokyo Hotel, a band. The relationships between the nodes are follows relationships. So, for instance, we can say this guy follows this guy. I don't know if you can see the arrows. This guy tweeted Georg, quote, if. This guy tweeted Georg Gustav. This guy, these 2 guys also follow each other, and they tweeted about the same thing. As you can see, it's not very clear what the actual propagation sequence is from this network, and we'll get to that later. That's where the formal modeling comes in. But it gives sort of at least a static picture of how the propagation sequence might have evolved. In this case, the picture is one of long chains rather than something like a star, where the information would have evolved or propagated very quickly through one set of the network, through one subset of the network. You can also see one long chain here, but most of the tweets were contained in this single star. Or another type we found is a sort of dense network that I call social, because more social networks are characterized by higher density. This one is about, I believe, Jennifer Aniston. And this one is interesting and especially complex to analyze because unlike a star or a chain where you generally know how the information could have traveled at least, you don't really know that, like this guy follows a whole bunch of people, is followed by a whole bunch of people, and, tweeted about Jennifer Aniston. Where this Twitter user was exposed to a rumor about Jennifer Aniston is not clear at all from this network structure. It could have been from any of their various neighbors. And overall, you can't really you can't really imagine how information would have propagated through this network because there's no clear pattern to it. There's no star pattern, there's no chain pattern. There's no clear start and no clear end. Right, so these are the kinds of Twitter networks we collected. We did not just collect social networks. I want to very quickly talk about a different kind of network that we collected, which is a keyword network. So here the nodes are not authors. Here the nodes are keywords. And this is collected not for a particular cluster, not for a particular rumor topic like here or here, but for all the rumor topics for one day. And so again, each node is a keyword, and there's an edge, an undirected edge between 2 nodes if they appear in the same tweet. What this shows is basically that the rumor topics in one day fall into distinct clusters. So we are actually getting at something that is not one giant jumble of information, but rather a set of distinct pieces of information that may or may not be propagating. This is probably a little small to see, but I'm just going to point some of these out. This giant cluster is Apple. Apple tends to generate a lot of buzz. And as you can see, it sort of has subclusters. This one's about the MacBook Air. This one's about the iPhone. This one's about the Apple Insider event. This one is about the iPad. There's a couple of more tech-related ones. This one's about the Google tablet, BlackBerry in the Netherlands. The ones that are not tech-related are generally about celebrities, Taylor Swift, Beyonce. I got a lot of information about who gets pregnant or may be getting pregnant, who's going out with whom. There's a giant cluster that is Justin Bieber, who gets a lot of attention on Twitter. Right, so this is one different network type that we collected. But,
sorry, could I ask?
Yeah.
I missed it. So an edge would represent what, like co-occurrence of a keyword within a tweet?
Yes. No, it's okay. Right. But now I want to go back to these propagation networks and puzzle out a little more about exactly what happens in these networks over time, exactly what the propagation sequence is. And to that end, I want to talk about formally representing rumors as pieces of information that diffuse over time. So why do we want a formal representation? First of all, we want to be able to compare rumors to each other. Second of all, as I mentioned earlier in the talk, we want to be able to extract common structural or information features to rumors versus other propagating information like news. And finally, this can lead to a generative model that describes how rumors start, propagate, and stop, that can allow us to make predictions either at a general or maybe even at a very specific level about how what a rumor's life cycle will look like. This is, of course, very important for anybody, for many people in the corporate world, but also all over, anybody in general who's interested in how rumors about them start, how to stop these rumors, and so on and so forth, how those rumors spread. Right, so again, some challenges. We want to, as I've said, encode both the information that's spreading and the diffusion pattern. We want to encode the notion of space and time. So to talk about space and time, something like this. Let's just assume that the rumor started somewhere here. And then it was, this guy's followed by these two people, and one of them tweeted about it, and so on and so forth. So temporally, we can talk about the evolution of the rumor, the propagation of the rumor. But we also want to talk about it spatially in terms of what sort of structures the rumor is propagating through and how far at any point the rumor is from the source, where far distance is defined in terms of some sort of graph distance measure. Those two, again, are not necessarily the same thing, and we do want to encode both. You can have very different pictures. For instance, with this star, it might be that first the rumor went here, 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 and there was this really long chain, and spatially this tweet is very distant from this tweet, or this user is very distant from this user. And that came early in the rumor's evolution. Or it may be that there was a starburst first, with lots of people tweeting about the rumor very close to the source, as we've identified it. And then there was this long chain. Okay, so we want to encode information and diffusion. We want to encode space and time. And finally, we want to be able to go from small-scale events to large-scale properties. By this, I mean the actual events whereby a rumor propagates are really small scale. Some guy or girl sees a tweet by somebody else and copies that tweet or tweets about a similar topic. But on a large scale, in combination, these events can lead to potentially very popular rumors, very damaging rumors, or very beneficial rumors. And we want to be able to emerge large-scale properties of the rumor, like the number of people who are talking about it, the total audience of the rumor, which is basically the number of people plus the set of all their followers, the length of time that the life cycle of the rumor in terms of time. We want to merge these from small-scale interactions. Okay. So what we want to represent is the propagation graph. We want to represent the temporal evolution of rumor as it propagates, in this case in the follower graph, and in the future in other graphs. We want to focus on propagation events that are tweets about that rumor, and we have the basic assumption that propagation can only proceed forwards in time. To that end, we can construct a formal representation of the propagation graph from atoms. There are two kinds of atoms I identify here. The start atoms, which are very simple. So first you have the start of the rumor. Some person tweeted about the rumor first, the start of the rumor on Twitter anyways. Then you have the start of a new cluster. This is a complexity and uncertainty issue. In the sort of ideal world, there is one anchor that initially starts off the rumor, some event, and then some small number of people first spread information about that event, and then that information goes from those people to those people's audience and spreads further and further. So ideally, the whole thing should look like a tree with one root. Because we are collecting data from Twitter, and these rumors may also spread outside of Twitter, and because we are not collecting census-level data, we have some uncertainty in how much data we've collected. We don't always get this nice idealistic picture. Instead, we can get multiple propagation clusters, basically multiple trees. So the start of a new cluster, whereas the start of the rumor is just the head, the very first person that we notice tweeting about a particular topic, the start of a new cluster is the very first person in a disconnected component in the propagation graph tweeted about this first. Right, so beyond the start, once the rumor has started in a particular cluster, it can propagate in one of three different ways. It can go in a one-hop fashion, sort of propagating in a line. So this person tweets about it at T1. They're followed by this person who tweets about it at T2, and then this person is followed by a person who tweets about it at T3. So we have a sort of linear hop pattern. A second pattern is a branch pattern, where you have this person tweeting about it initially at T4, and they're followed by two people who tweet about it at T5 and T6 respectively. So in this case, it's a fan out rather than a hop. Finally, overlap, you have some person who tweets about it first at T7, and then some person follows them, tweets about it at T8, and this person at T9 follows both the person who tweeted about T7 and the person who tweeted about T8. There's the overlap structure implies some uncertainty because we don't know where T9 heard the information from. And if you think about these atoms, they were inspired, obviously, and map onto generally the three large types of graphs we saw. So a chain graph will have lots of one-hop propagations. A star graph will have lots of branch propagations. And a social graph will have lots of overlap propagation of atoms. Okay, so we've got these atoms. Now, how do we construct the rumor out of them? Well, very simply, you concatenate the atoms in temporal order. So here I make a simplifying assumption in that I look at the entire graph at some final point in time. So I don't know, there's like roughly 50 time points here, and I looked at the graph here, and this is what it looks like. And then I identify the atoms based on this graph. This is not the same as identifying the atoms in the order based on the graph that is when the atom appears. So like this guy, so we have start atom here, then new cluster. So like let's say it started here, then some new cluster happened here, and then we have a branch event here. So when this branch event first happened, there was only the one node. So we're possibly identifying the branch event by this node. At this point, there's only one person who follows the starter, and there is no branch. But later on, there will be a branch, and we're accounting for that. I'm not sure if this is exactly the right way to do it. This is what I'm doing for now, because otherwise you have uncertainty either way. Because otherwise you can have something that is initially a one hop and then later turns into a branch. But this is something we're still investigating. Anyway, to get back to the large scale picture, we concatenate the propagation atoms over time, and we have this long string that we can now compare to other strings, and that is sort of some of the next steps of our research. And then we have the corresponding propagation graph. As I've been saying throughout this talk, it's not clear how you reconstruct the graph from the string. You don't know the actual order. The order is encoded here, but there's no sort of graphical representation here. This is a formal representation. The structure is encoded here, but not the order. And one way to get across that hurdle and to actually visualize both the structure of the graph and the order of propagation is a movie. So I'm going to show you guys this. Nothing happens at first. So this is just the same, in fact, I think the exact same graph as here, except we're going to see the nodes and their edges appear over time. Initially, all of the, only one node appears, the person who tweeted about it first, and then new nodes appear as new authors tweet about the Rumour topic. So as you can see, at first not a lot happens, then another person tweets, then another, and the thing slowly begins to grow. As you can see, the graph misleads us with respect to the order of propagation. The graph makes it look like one nice, or like a set of nice chains. In fact, there's a lot of independent events, as people probably learn about the Rumour from outside of Twitter. A lot of these isolates basically are people who have tweeted about the Rumour that are unconnected to anybody else who has tweeted about the Rumour previously. They may be connected to people who tweet about it later on, but none of their followers or followees has yet tweeted about the Rumour. So this thing keeps growing. Wow. Okay. Just fast forward this. There we go. I want to get to the very end here. So you can see the long branching structure slowly being constructed over time. And here I want to draw your guys' attention to a whole bunch of people who tweet about this Rumour. This is a Rumour about SNSD band and their upcoming third Korean concert. And we have a bunch of people who tweet about it but are disconnected, but are part of this graph, and all of a sudden they're connected by this star. And this is the star I wanted to draw your guys' attention to, so I'm not going to go back to the moon. So this is a person who follows a whole bunch of people who tweeted about the Rumour, but has not tweeted about it herself for a really long time, until almost the very end of the propagation sequence we've captured. And it's interesting to find out, and these events are somewhat anomalous. Why is it the case that she has all of these followers but has not tweeted about the rumor herself? Looking at her tweets, we find out that, in fact, this person was trying to counter the spread of rumor and trying to avoid talking about it. And when she finally sort of gives in and talks about it, she says, guys, please don't spread any rumors on SNSD third Korean album, Japanese album from March 2011. It's not announced yet. So we couldn't have seen that from just the static graph, but the dynamic picture of propagation revealed this anomalous event to us and allowed us to identify it. So the very last thing I want to talk about is now that we have these strings, we can also begin to analyze them. These are just some very, very recent results. So we can, for instance, look at the transition probabilities between the strings. So this is a standard transition probability matrix, and over all of the data we have collected, basically how many times did a C atom followed by another C atom? So how many times did it jump from one cluster to another without any connections? How many times was it followed by an H atom, and so on? How many times were all of these followed by a C atom? So at the bottom I did the sums, which basically show very simply that C and H are heavy attractor states. So very frequently you have things being followed by the appearance of a new cluster, and when that's not the case, very frequently you have things being followed by hops. So this means that a lot of the time either the information propagates independently of the network, either outside Twitter through connections we haven't found, or it propagates in this branching manner. Much less frequently does it propagate through branch and overlap atoms. So with that, I have taken up, I believe, all of the time I have, maybe a couple minutes for questions. But first I want to thank Natasha, Jürgen, Milan, Gabriella, and everyone else who consulted, provided data, and helped with this project. Thank you very much.
Good. I have time for questions.
Yes?
So what's the probability distribution of the number of tweets per topic and number of users per topic? Is it a long tail or is it some other thing?
It is a long tail. Most of the distributions I haven't talked about because they're mostly long tail. Many topics, as one would expect, don't become very popular and are not really followed up, so they have only a couple of tweets or a couple of users. A few become really, really popular. I think the most we've gotten is so far is about 1,000 tweets. Yes, 1,000 tweets for a single topic out of the 80,000 tweets that we have collected total. Yes?
Do you think using your model you would be able to infer whether, I mean it's hard to find ground truth data about that, but whether a tweet was sourced from Twitter and not from an external source of media and then propagated through Twitter?
Right. So I think that should be possible. One thing we have is very rich data that we have collected. So we have things like whether a tweet contains a URL, in which case it's much easier to say, if this tweet links to CNN.com, then clearly the information came from outside Twitter. So I don't know about with perfect certainty, but yes, we can probably say something with a likelihood, okay, this probably came from another Twitter user, or this came from outside of Twitter. Yes?
Yeah. About your string representation, so is the order of the atoms in the string, I presume, is sort of absolute time?
Yes, ordinal time, yeah.
But what about events that kind of might happen independently? So like you might have a hop created over here, but a branch created over in a different sector. It might happen afterwards temporarily, but they might as well just have been interchanged because they don't have any influence on each other. Would that mess up your transition probabilities?
Right. So I think at the small scale, yes, it does. I think when you aggregate, we don't have a particularly large scale here, but we do have access to more data. And when you do this sort of thing over thousands, tens of thousands, hundreds of thousands of tweets, you get order out of the data. I would see those sorts of things as noise, and you'll get a certain amount of noise in this model. But as you have more and more scale, if there is an order, then it should emerge out of the noise.
And so alternatively, one can do much finer level encoding. So if you know that the C started, and then you can call it C1, and then when B started, then you can see whether B is associated with C1, then you can do B1 coding instead of just B. So I guess what you're saying, if you kept track of where the attachment happened, and also what you're saying, if you just you can look at the time scale, and then we can talk about the activation energy where each of the hops would happen. So you can, first coding can be on the level of attachment, and second one can be on a fine level of time measurement. So I fully appreciate it, yes.
Yes.
Any other questions?
Yes.
Did you see any correlation between usual influence user metrics, like number of followers, number of retweets, and the role they have in these propagation graphs?
No, and in fact, so I haven't looked at number of retweet. Actually, I believe I have looked at the number of retweets, and I don't think I saw a correlation. I did do some basic statistical analysis on this data. There was nothing particularly interesting to report because the biggest significant results were like if a user is statistically more likely to be retweeted if they have retweeted themselves, or if their link includes a tweet, which are interesting results, but they've been reported on before. Yes.
I think it's a lot of activity that, for example, in the network, in the movie that you show.
Yes.
And all the edges of rumors about specific topics, so to speak.
Yes.
And I guess that during this time, those users generate more tweets, not about this topic.
That's right. Yes.
So and you didn't show them.
Right.
So what are the percentage of amount of tweets compared to for a certain topic, for example, the one you showed, compared to the general baseline activity?
I think for a particular topic, it's usually the baseline is pretty small, and then it can spike to be really high. This is drawing on previous work by others like Yuri Leskovic, who basically showed that most information follows this very spiky pattern.
No.
Yeah.
My question is more about how many tweets altogether the group generates?
Yeah.
How many for a certain topic?
Right. We're talking probably around like 1% overall. So 1% for a particular topic out of all of their tweets.
And that is based on the coding that I didn't mention at the beginning, but we did some manual coding of a sample just to identify what type of tweets people engage with. And then based on the manual coding of the type of tweets, I think the measurement was only less than 1%.
Yeah.
Actually rumor related. And then the separate coding was done on the rumors themselves. So
Yes.
the sample of rumors themselves, then we did another coding. But we didn't talk about this. It's about taxonomy of types of tweets. That can give more insight into what you were saying.
Yes.
Can I look at the entropy rate of the atoms?
Say again?
Can I look at the entropy rate of the atoms?
The entropy rate over time. No, I haven't looked at that yet. I think that would be very interesting. Yeah. Yeah, no, I think that's absolutely something to look at. Sorry, you? Yeah.
So I think the main goal could be predicting the size size of the rumor propagation? Is it right?
Right. I mean, so that would be among the main goals. I think one of the things I talked about is I want to be able to predict or emerge these large-scale properties like cluster size from, from the model, which is based on small-scale events.
So you're distinguished into three different structures like chain, star, and the social?
Yeah.
No. One whole branching and the overlapping.
Yes.
Overlap. And I don't know why you actually distinguish those into three categories. What's the purpose for doing that? Do you want to find some graph structure for the rumor propagation?
Right. So certainly we think that finding the motifs, graph motifs on the propagation network will help us predict, will help us make a better model. But there's also sort of intrinsic reasons for collecting for making the model focus on these different structures. So when these different structures imply a different sort of general propagation path, when it goes from one person to another, that means that it's basically that you don't need a lot of reinforcement. That means that the network is spreading through a very sparse and long structure. This means that the message passes on very easily. Somebody sees it, they copy it. Another person sees it, they copy it. This is in contrast to many models, or to some existing models, that imply that you need reinforcement to pass on a rumor. And reinforcement would correspond to the overlap structure. And finally, the branching structure implies that one person has a lot of influence in the network. So something like a celebrity or a star. Yes?
At the time to die of the rumor, look at that. So for example, the rumor might only be relevant for say 2 days. Doesn't actually get to some of the network in that time, then it's not going to propagate after that.
Right. So actually, timing is a very important issue here. Most of these are extremely short time scale. I don't have a full chart that describes the distribution, but we're talking about the scale of hours, and a lot of the activity often happens on the scale of minutes. So in this graph, it goes, you saw that nothing was happening for a while, and that was like a few hours collapsed. And then a lot of the activity, a lot of the propagation happened within literally like 15 minutes as it spread like wildfire. So yes.
Maybe that's all the other people in the network waking up in the morning.
Oh yeah, it absolutely could be. I haven't correlated that with some absolute time level. I would say that's an interesting hypothesis to test. From other projects I've done, it just seems to me that information propagates very quickly on Twitter. So yes, while a lot of these things do die out within a couple of days, they can reach within those couple of days very, very large audiences.
What about say for links in that network who might not be logged on at a particular time? So somebody who really who would propagate that message, they haven't seen it because they're simply not on Twitter.
Right.
Maybe an hour later.
Right.
And then they propagate the message and suddenly you see a whole new branch or forest appearing in the ground.
That would imply some sort of cyclical aspect to the propagation, to sort of the timescale of propagation, which I haven't seen, but there's some really interesting work that is being done by Scott Golder right now at Cornell that is looking at these very patterns, and it would be interesting to basically use his methods on this data, because yes, we have the timestamp of all timestamps for every tweet, and we could check whether that's going on.
You can also check as well what other tweets various people in the network have actually sent. If they sent a tweet
Yeah.
on another topic, not this particular topic,
Yeah.
then they're obviously logged on, but they're just ignoring it.
Right. That's true. Yeah.
Maybe I should comment on this. There was lots of thinking about what to use as a structure to show the propagation of the tweets. In this example, the way representation is done, underlying structure is the follower network. And on top of it is the links that have been activated, plus the ones that could have potentially caused the tweet to be seen and retweeted. So on this graph, for sure, this person here doesn't have a follower in the overlap. Because there are a number of hops here.
Yeah.
Otherwise, we would have put a link, we would put an arrow showing it. So now you can see that, in fact, it takes some time, and it's a design of the Twitter, in particular medium, that requires a certain activation energy at every follower's kind of sphere. And it has to get enough of the overlap to get to these people over there. That's one thing. Or we are counting on the general broadcast mechanism in Twitter, which, as you know, because of different user interfaces, is very unlikely to influence people, because people may miss it. You know, if they're asleep at that moment, they won't see it among the top 10. So in a way, we are relying upon the other part of the design of Twitter, which will be this propagation through the follower. Yeah. And the inverse star here is very interesting, is demonstrate what Vlad was saying, the activation required for somebody to react. So the person who was in the follower list of all these, in a circle, did not react until decided to counterattack Twitter. And the fundamental question also Vlad was pointing out is how do you, in order to counterattack this, she didn't have any other effective mechanism but to tweet herself, which could have gone in the wrong direction, started another rumor, just to say. So in a way, thinking of a back channel that would neutralize a tweet. Maybe also, Vlad pointed to me, there is the F reply, of course. Then you can start sending to each individual, say, shut up, don't talk anymore about this. Yeah. So in a way, understanding whether the same mechanism that they use for rumoring can be used to neutralize them. That's one question. The second question is how to get the connectivity, keeping into account the follower network, the probability of somebody retweeting or the activation energy that is required to kind of give it a boost.
Yes?
Does the API tell you, I mean, you're inferring everything from just doing the tag analysis, keyword analysis with the actual content of the tweets, right?
Right.
But you actually, at least in theory, have the temporal sequence of people starting to follow someone separately. And I know, obviously, if I choose to follow you and then I choose to follow you, that's a minor event compared with me then retweeting or not. But it might be interesting to know if the temporal graph that describes the order and structure in which people place their position in the Twitter graph actually has an influence on their role in spreading rumors. So whether they become a splitter, repeater,
right,
or a branch point, for example, or an overlap point. So you might be able to see if there's some approximation to those same structures in the order of becoming a follower or being followed.
Oh, that's interesting.
Then that might tell you, give you a predictor, and it might be different than purely something like degree.
Right. No, that's actually a very interesting way to look at it. Generally, no. I mean, and there's been some research also out of Cornell that looks at the order of people following each other, but not in the context of diffusion. So yeah, that would be interesting. I wonder if then following some people in a different order implies some sort of social preference.
Yeah, I'm just wondering if somebody who sort of joins in a starburst of
Yeah.
a lot of people naturally becomes a harvest in flipping that relationship around, or the opposite. I don't know. I don't have any hypothesis to grind there.
Yeah. Thanks.